Today, our topic is string cipher and block cipher. ഈ string cipher and block cipher ആദ്യത്തെ ലെസണിൽ നമ്മൾ ഓൾറെഡി ഒന്ന് കണ്ടതാണ്. Okay, today we are going to continue with block ciphers, modes of operation. Cipher and modes of operation. Some of them are block cipher and some of them are string cipher. So, അതിനു വേണ്ടിയിട്ട് we are going to look at string cipher and block cipher with some emphasis on modes of operation. Okay, and then we will go in to discuss the actual modes of operation. Now, block cipher and string cipher both converts plain text to cipher text. But in block cipher, you are going to convert a block of data at a time. So not one byte, multiple bytes at a time will be converted from plain text to cipher text. Usually, it is either 64 bits or more, whereas in string cipher, it's 8 bits, 1 byte. Okay, in the case of block cipher, the complexity of the algorithm is less compared to string cipher. In the case of block cipher, diffusion is used as well as confusion. That means it can be both substitution and transformation, combinations of both. Whereas in string cipher, mostly it is confusion that is being used. So it is, the replacing one alphabet with another, or replacing a few, groups of alphabets with others. Now, in block cipher, reverse encryption is hard. It's not so simple. Whereas in string cipher, cryptanalysis is easier to do. Now, what we are more interested in is the modes of operation that is usually used for block cipher and string cipher. The ECB and CBC modes, that is electronic code book and cipher blockchain, is used for block ciphers, whereas CFB and OFB, cipher feedback and output feedback, is used for string cipher. Other than these four, there is one more mode of operation which we are going to look at, that is counter. Okay, it's similar to OFB with a small difference. Then examples of block cipher are rail fence technique, columnar transposition technique, etc. Transposition techniques are used, whereas in string cipher, substitution like Cipher, polygram substitution, etc. are string ciphers. Block cipher is slow compared to string cipher. Okay, the next thing is that applications that require strong encryption will normally be using block ciphers, whereas if the strong encryption is not required for large transmissions, then string cipher can be used. But in the case of both block cipher and string cipher, there are occasions when it is used for file storage and internet communication in both cases. Okay, then the block cipher is considered more secure than string cipher because, depending on what key we are using, we can use the same key multiple times. Okay, whereas in the case of block cipher, we can use different keys for different types of encryption. So in that case, it is like string cipher is less secure than block cipher because keys are normally repeated. Okay, typical key length is 128 or 256 in both cases, and the block cipher operates on fixed length block data, whereas string cipher is taken 1 bit at a time, so any length. And block cipher, the modes of operation are used so that the block cipher can be repeated multiple times for different blocks of the same message. So if it is a large message or a small message, block cipher can be used. Just that repetition of the mode will be used to incorporate all the bytes in the message. Okay, ini modern block ciphers are normally used for cryptographic, most widely block ciphers are cryptographic algorithms in use. Then what it provides is secrecy, that is, the data is going to be kept confidential, and authentication, that is digital signatures use authentication. Okay, and normally we are going to look at the module 2, we are going to look at symmetric algorithms, cryptographic algorithms, and we will be using it as, we will be looking at asymmetric cryptographic algorithms or public key ciphers, okay, in the third module. So in both cases, you will see that basically block ciphers, symmetric cryptographic feistal cipher structure using. So we are just going to introduce what is feistal cipher structure. Okay, now feistal cipher structure and the structure itself is based on Shannon structure. Okay, a researcher called Shannon, he has proposed in 1945 a model in which, instead of using, we saw earlier that in transposition algorithms, basically diffusion is used, and in stream algorithm, confusion is used. Okay, so instead of using just confusion or diffusion, why not use both? That was the proposal. Okay, now what is confusion? Confusion produces a complex relationship between the ciphertext and the encryption. So it's based on a function, the encryption is done. And this is normally done using substitution. Whereas diffusion is a complex relationship between the plain text and the ciphertext. And this is a permutation algorithm. So it is rearranging the alphabets in the particular plain text to make it difficult to decrypt it. Okay, so this is, as we know, permutation changes the order. The feistal cipher proposed a structure that implements both confusion and diffusion, that is substitution and permutation alternately. Now this is, if you can see on, look at my cursor, the left hand side is the encryption of the algorithm, and the right hand side is the decryptions from ciphertext to plain text, and here it is from plain text to ciphertext. Okay, so you can see over here in this section, okay, the plain text is divided into left side and right side. So if you have 64 bits, 32, it will be divided into, and the right side alone is used for a substitution algorithm. So it's a symmetric algorithm. Key K1 is used, a function, it is given to a function, and that output is XORed with the left-hand side to give the next RE1. Okay, so in this step, this XOR step, we have got the diffusion, and in the function F step, we have got the substitution, and this is done multiple times. So you can see over here, we have got 16 rounds. And then the final ciphertext is so now, because there's a combination of substitution and diffusion, it becomes much more difficult to do any sort of cryptanalysis easily. Okay, and the process which we have done from plain text to ciphertext is reversed so that we get the ciphertext from the plain text. Sorry, from the plain text from the ciphertext. So over here you can see the first step that was done over here is that that is the ciphertext is RE17. This was the last step. So LE16 and RE16 were interchanged to give LE17 and RE17. So you can see over here, the RE17 is actually LE16, and LE So you can see that the first step is we are interchanging, the right-hand side is made the left-hand side, and the left-hand side is made the right-hand side. So this last step has already been done over here. And then what we are doing is reversing this, but to get RE1, we needed to do the function and the XOR. So that particular step, we are using the function keys. K16 is the key that has been used, and the XOR is done using the left hand side, that is RE16 is used for the XOR. So now we have got the previous LE15, and this is repeated. That is, whatever we did in the previous steps, we are reversing in the decryption step to get the plain text. Okay, so now this is the structure that is going to be used for symmetric ciphers, which we will look at. DES is one of the symmetric ciphers that uses this pastel structure. Okay, now we are going to look at modes of operation. I already told you that modes of operation is required because normally the algorithm is for a 64-bit encryption or a 128-bit encryption. In the case of DES, it is 64-bit, and in the case of AES, Advanced Encryption Standard, it is 128 bits. Okay, but problem is that none of our messages are just 64 bits or 128 bits exactly. It's either longer or shorter. So how do we accommodate those messages which do not have this exact size? That is where modes of operation come in. So longer messages will be broken into this size, 64 bits if we are using DES, and 128 bits if we are using AES. Okay, in the case of shorter, like when the whole message is divided, the last block will probably not have exactly 64 bits or 128 bits. So we will use a padding so that it will be made into 64 bits or 128 bits, depending on the algorithm. And then we will be using these modes of operation. We are going to look at the 5 modes of operation, and these modes of operation. These modes of operation were actually, suggested or defined by NIST. Okay, National Institute of Standards it is in the USA, and they are the ones who defined how ECB, CBC, CFB, OFB, and CTR counter should work. So we're going to look at each of them one at a time. Okay, so the modes of operation, I've already told you these things, that the encryption for DES, it encrypts 64-bit blocks and the key size is 56 bits. Okay, so we need a way to encrypt or decrypt arbitrary amounts of data, and for that we are using these different modes. Okay, now in the ECB mode, electronic code book ECB mode, what we have is, see, this is the encryption. Okay, it's just like a code book. So if we take one particular block of plain text, that block of plain text will always be mapped to one particular cipher text. That is why it is called an electronic code book. So you can see over here, one particular key K1 is used, and DES is directly applied on plain text. So it is a symmetric key. So when you're decrypting also, you will use K1 on CI and you will get PI. Okay, now if we have got large size of data, simply what we are going to do is divide the whole message into 64-bit blocks, and then the same operation is done for all those blocks to get the cipher of the whole text. And decryption is done by, again, using the same key with the decryption algorithm of DES. Okay, so this is how electronic code book functions. Now, what are the advantages and limitations? One, as you can know itself, the electronic code book, for the same plain text, if a block of plain text is same, then the same cipher will be there every time it appears in the message. Okay, and that is the disadvantage. And to overcome this disadvantage, the other modes had been designed. Okay, the weakness is because the encryption message block is independent. Each block is separately being encrypted. And that is why the repetition also occurs. Okay, so we are going to look at what can be done. CBC is Cipher blockchaining. So instead of having independent encryption and decryption blocks, we are going to chain it in such a way that there is a relationship between the previous block and the next block. Okay, and see, this is what is done for Cipher blockchain. Now, in the case of Cipher blockchaining, we require a special value called initial value, IV. Okay, why do we require IV? Because the cipher is got by first the plain text is XORed with the previous cipher text. Okay, so for the first block, we don't have a previous cipher text. So for that, we require an initial vector. Okay, so that P1 is XORed with C0, the initial vector, to get, and then this is applied on that particular value to get the resultant cipher. Okay, so now the problem that we had earlier, where if we have a particular block of message repeating in the particular message, the same cipher is got, and it makes crypto analysis easier. Okay, so now that problem is solved, because even though the block is the same, the previous cipher is going to affect the cipher of the next block. So it is unlikely that the same cipher you will get for even similar blocks of messages. Okay, so this is used for bulk data encryption and authentication. This is what is done. The same thing that we saw in mathematical form. What is being done in the first block of encryption, IV is first XORed with P1, and that value is encrypted using this and the key K to give C1. And now this C1, in the next case, this cipher is going to be XORed with the plain text, and this continues for all the blocks of the message. In the case of decryption, first C1 is decrypted, and then once again, A XOR A gets cancelled. So when again IV is XORed with that decrypted C1, we get the original P1. And here again, symmetric, so K is the same. Okay, so this is continued to get, and each time the previous cipher is given as the input to the XOR. Okay, so it reverses the process. Okay, now this is the proof for the CBC working. We saw already that a particular cipher CJ is equal to the encryption using key K of this previous cipher plus the current plain text. So now, if on both sides we do decryption, we get the decryption of CJ is equal to decryption of encryption of CJ plus PJ. Decryption of the encryption means you will get CJ XOR PJ. Okay, so decryption of CJ will give you the CJ minus 1 XOR okay, so now you can see that we get, when we decrypt the CJ, the cipher, we get the previous cipher XOR the plain text. Now we need to remove the this is XOR CJ minus 1 XOR PJ minus 1 to get the plain text. If we XOR once again CJ minus 1 over here, so we get CJ minus 1 plus the decrypted value will give me the plain text. Okay, so from the decrypted value, when that is what we saw over here, the decrypted value, you XOR the previous cipher and you get the plain text. So this is the proof. Okay, now what are the advantages and limitations? Here, the disadvantage that was there in ECB has been solved. Okay, but the problem is the initial value must be known both to the sender and the. So you can see that the initial value must be sent to both the sender and the receiver, and if it is sent in clear, then already if there is an attack, the IV will be compromised and that will compromise the whole structure. Okay, the IV can be either a fixed value or it must be sent as encrypted in any other mode, ECB mode or something. Then short messages are needed to be sent. Normally ECB is used. So this can be sent using ECB before the encryption of the rest of the message. Okay, so one secure method must be used to transmit the initialization method. That's the limitation of CBC. Okay, now CFB is Cipher feedback. CFB is Cipher feedback. This feedback is, earlier we had given feedback of the Cipher, okay, to the next block. Here, to each block, the Cipher is going to be added. A part of the Cipher is going to be added to the next block of data. That's why the name is feedback. And this particular standard can be implemented in stream mode or in block mode. Okay, so 1 bit, 8 bits, that is a byte, or 64 bits or 128 bit, all that can be done. But you'll see later, it says that the CFB 64 and 128 are more secure than 1 and 8. Okay, now what is being done over here? The encryption is not being done on the plain text. Instead, the cipher is being previous cipher is being encrypted with the des value. Okay, and then plain text is simply being XORed with this particular cipher text. This is the difference. And this can be done for stream data encryption, and for authentication purpose, this can be used. So now look over here. The first C0 value is IV. Okay, this IV is divided into 60. It is a 64. This part is 64 plus S bits. Okay, so the 64 bit value, the 64 plus S bit value is the IV value, and this left side 64 bit is being encrypted with K, and that 64 bit is going to be given over here as input. Okay, this 64 bits is being given as input, and only the first S bits of this 64 bit is being taken for the plain text to be XORed. So now it means that this S bits is the size of the message that is being divided. So it is not a 64-bit message that is block. It is an S-bit message block. Okay, and then the cipher of this particular value is then given to, that is, it is put in this S bits and it is left shifted. So again, the 64 bits is taken, encrypted, and this process keeps continuing. Okay, now you can see, since the encryption is being done for the IV and the previous cipher only, the actual plain text does not have any encryption process. So the encryption, des encryption itself is used both in the decryption and in the encryption. And this particular section is same for both encryption and decryption. So this part can be calculated beforehand itself. Okay, the only difference over here is that the first cipher needs to be given this S value, and the first cipher is given as input and XOR to get the plain text. Okay, because the IV is not used over here. Here we are using the S values to XOR. Okay, so this is slightly different from the previous methods. Now, in the case, this is cipher is being fed back to the initial value for the encryption. Okay, in the next one, you have OFB, where the output will be fed back. We will be looking at that. What are the advantages and disadvantages? Okay, this method is appropriate when data is arriving in bits or bytes. So this particular method is more suitable for stream mode. Okay, the limitation is that we need to, stall the while do block encryption after every n bits, because each time we need that particular cipher value to be given to the next one. So unless we get all those bits, we will not be able to send it forward. Okay, give the feedback. Okay, and the note that the block cipher is used in encryption mode at both ends. So you see the des is used in encryption mode in both cases. We saw that. Okay. Now the problem over here is that this plain text plus this the XOR the S bits is C1. So if there is an error in any one plain text, that error will be propagated throughout the encryption, throughout the message. Okay, that is the disadvantage, and to solve this problem, OFB is used. Okay, now let's look at what is happening with OFB. We have the output of Cipher is added to the message. The output of the Cipher is added to the message. Okay, so feedback is independent of the actual message. What is output? Output is first the initial value. So earlier, what we had in CFP, this section, there is where we're getting the output for OFB. Okay, so first output is IV. That output is given to the for the first output, O1. Des of IV is O1, and that is XORed with P1 to give C1. So P1 is not being propagated, instead OI is being propagated. So if we have the IV value correct, then even if there is an error in one block of the plain text, it will not be propagated throughout the message. And this is normally used in noisy channels. Why? If there is an error in the message that is being transmitted, the original plain text, that means there was some sort of noise induced. So if the channel is noisy, it is better to use OFB. Okay, so now over here you can see similar to the CFB mode. Only difference is that IV is being used, and the output of this encryption S, instead of taking from C, from this output itself, it is being given over here. So this section is totally independent of the plain text and cipher. And this again, like earlier, encryption is being used in both decryption and encryption, and the S value, this particular value which is being propagated, is not dependent on the plain text or the cipher text. Okay, so the decryption, the previous problem has been. Now we're going to look at the advantages and limitations of OFB. Okay, now you can see that errors do not propagate, so that's an advantage. Okay, it is more vulnerable to message stream modification. Okay, so if we use the key plus ID sequence, reuse it, then it is possible that the message can be modified and the cipher can be changed. Okay, so both the sender and the receiver must always be in sync, and the originally specified M bit feedback, it must, that is this bit feedback, that specified feedback must be synchronized for both the sender and the receiver. Okay, so after the subsequent researchers proved that this has got a problem, the CFB method, full block transmission feedback method, has got a problem, and CFP 64 or CFP 128 is the only one that should be used. Okay, so it is better not to use these methods for stream transfer. Okay, now we have the counter method. This is similar to the OFB method with one difference, that there is the IV value is one value, and each time, instead of finding out giving the feedback where the next value is going to be counter plus 1. Okay, and then that output, just like OFB, is XORed with PI to give you the value, and this is normally used. The feedback is not required. We don't need to wait for the N bits to come. Okay, so high-speed encryption, when it is required on a network, counter method is used. So you see, now there is no feedbacks over here. So there is no FB over here. Each time the encryption is done using the counter value. This first counter value alone is set, and then each. So now you can see that the encryption over here can be done independently and it can be done simultaneously. Once this counter value is known, then counter +1, +2, +3 can be done, and this much section can be done previously, and then just XOR the plain text with that particular encryption to give the ciphertext and reverse it for the decryption. Now, if you notice, in both the feedback methods and in this counter method, both the encryption and the decryption is separate from the DES encryption. So encryption is used in all these three methods. Okay. Now, what are the efficiency is that parallelly, both using hardware and software, we can calculate the first part. Okay, that is where the speed in encryption comes in. And you can randomly access the encrypted data blocks and do the encryption. It provides good security. And the only thing is that once a particular counter value has been used, just like in the previous OFB method, don't reuse that same counter value. Randomly generate the first counter value and use it for different encryption so that it cannot be broken easily. Okay, now this we have already discussed. Please look at it here. What I am actually interested in is what are the typical applications for each of the modes. ECB is for secure transmission of single values or small messages. Okay, here there is general purpose block-oriented transmission plus authentication. Here also general purpose stream-oriented transmission with authentication. And then we have stream-oriented transmission over noisy channel. And finally, we have block-oriented transmission with high-speed encryption. Okay, so these are the applications. With this, I would like to stop today's lesson.